Hello everyone, this is Jim Corkins again, and we are continuing on with this is going to be the end of our review of trigonometry and addition of vectors, and now we're going to actually apply it to velocity vectors, acceleration vectors, and displacement vectors. Okay, so we're going to talk about what's the relationship between all of those vectors with regards to addition of vectors and also trigonometry. So if you haven't done the reading, again, please go, if you have the Coletta textbook, please do read chapters 1, 2, and 3. In OpenStax, if you are in Physics 111, chapters 2 and 3. And if you're in Physics 121, OpenStax 2, 3, and 4. All right, and also probably start, if you haven't started on your homework, please go ahead and start on the homework, and I have the homework assignments related to this listed here. Okay, so here is a problem where you're given an initial velocity vector and you're given a final velocity vector. Okay, and you have to find out what is the acceleration vector from these two vectors. Okay, so what I want you to do is go ahead and take a shot at this problem, and let's see how you do. Okay, and what we're going to then do is discuss tactics on how to do these type of vector addition problems to solve, given a initial velocity vector, a final velocity vector, how do you find the acceleration vector, how do you find the displacement vector? And we kind of already did this in one dimension back earlier in one-dimensional motion, but now we're going to apply it in 2 dimensions. So go ahead and pause the video and try to see if you could find out what the acceleration vector is here. Okay? All right, so let's think about this problem a little bit. And what I'm going to do is actually I'm going to show you a couple things. All right? So here we go. The average, so what this slide is basically saying is the average acceleration vector is the direction of the change in velocity. So what they are saying is this. I'm going to mark up the document. So they're saying, so remember that equation of motion, which is the velocity versus time linear fit that we were talking, that we've done before, which was v final equals v initial plus acceleration delta t. Well, what they're saying is if I subtract the initial velocity vector onto the other side, you get v final minus v initial, and that is equal to acceleration delta t. And so delta v is equal to the acceleration delta t. And I should put vectors on these, especially since we're talking about vectors. So and then, so when you solve for acceleration here, actually, when you solve for acceleration, you get this, okay? So in this problem, so here you have a problem where you're given an initial velocity vector, okay? And I'm going to overlay a vector on top of this, and I'm going to use green to be my initial velocity vector. Okay, so here's the initial velocity vector. I just measured it out, and then I'm going to label it VI. All right. So this is my initial velocity vector. Well, if you have a final velocity vector that is given just like this, and I'm going to use blue for final velocity. And got to remember to do the borders as well. Okay, so here's the final velocity vector, okay, which now we have our other problem. Okay, well, here's the problem with this. If you want to get the resultant of this, and let me go ahead and draw that here. This resultant vector Okay, so this is the positive initial velocity vector, and I should put that in front here. Oh, come on. This is the positive initial velocity vector, right? And this is the positive final velocity vector. Right, so by adding these two together, you're basically getting just v final plus v initial, all right? V final plus v initial, right? Which is fine if you want to do that kind of stuff. And I'm going to use black as the resultant vector of this, right? But that doesn't help us, because what we have to do is we have to subtract the initial velocity vector from the final velocity vector, right? And we've done that before, okay? So in order to do what we need to do to manipulate this, we need to reverse this initial velocity vector. So what I'm going to do is I'm actually going to take this overlay again, this initial velocity vector on top of this, and I'm going to actually reverse it, okay? And so once we've got that reversed, okay, well now we're going to have to restructure some things, right? Because we have to subtract the initial velocity vector from the final velocity vector. Okay, so I'm looking at this equation right here. So this now, since I've reversed it, is now the negative initial velocity vector. Okay, and this is still the positive velocity vector. Well, this is not the resultant vector of this vector subtraction anymore. Okay, this will be the resultant of the vector subtraction. Again, to add a negative initial velocity vector to a positive final velocity vector, you start, here's where the start is. So the start is right here. I'll mark it. So the resultant vector goes from start to end. So you started here, you moved down and to the left over the period of 0 seconds to 1 second. And then from 1 second to 2 seconds, you then moved down and to the right. Okay, and that's the positive final velocity vector, okay? Well, sort of, kind of, you actually did up and to the right and then down and to the right. But anyways, the point is that this right here, this is the resultant vector which is actually v final minus v initial. It is delta v. This is the change in velocity vector. And that is delta and then v. And I'm going to change this to a symbol. Can I change it to a symbol? There we go. There we go. Now it's delta v. So notice this is now delta v. Okay? Well, the delta v vector is the acceleration vector too, right? Well, it's actually acceleration delta t, but my point is the delta v vector is the acceleration vector too, right? So I'm going to now call this equal to acceleration delta t. And I'm going to drop this down to symbol. Right? So what we had to do is we had to identify the initial velocity vector, which is a positive initial velocity vector, right? And this is the positive final velocity vector. And so by reversing the initial velocity vector, okay, all right, so by reversing that initial velocity vector, which is what we did right here, and then adding that reversed initial velocity vector to the final velocity vector, what we get here is we get a change in the velocity vector, which is delta v, which is actually the acceleration vector as well. Okay? Because v final minus v initial is equal to delta v, and delta v is equal to acceleration delta t. So essentially that's what we're going to do. So when we go on to the process, and this process is laid out in Knight's textbook, what you're going to do is over the period of over time interval, you have an initial velocity vector, and then you have a final velocity vector. What you're supposed to do is take that initial velocity vector and then reverse it, and then when you add that reversed initial velocity vector to the final velocity vector, you'll get a change in the velocity vector, and that change in that velocity vector is acceleration times delta t. Okay? So back to our original problem, here we go. What we're going to do is we're going to go ahead and take an arrow, and we're going to measure out this, which is our final velocity vector. Okay, so here's our final velocity vector. And then I'm going to measure out an initial velocity vector, which is going to go and I'm going to reverse that. So this is the initial velocity vector that has been reversed. Okay. And this is going to be v final, and it is, we're going to just use black. Okay, so this is a positive v final, and we're going to add to that, the initial, which is the negative initial velocity vector. Okay. Okay. And so the result of that, the resultant of this addition, well actually it's vector subtraction that we're doing, is going to be delta t. So you started here, you're going to end here. You started here, you walked up and to the left, up and to the right. That is actual the motion vectors, right? So this is going to take place, oops, let me get rid of that. This is going to take place over 0 seconds. That's the start. 1 second, and then 2 seconds. Okay, so actually I should have marked it over here. I apologize. 0 seconds, 1 second, 2 seconds, right? And so the resultant vector of this, vector subtraction, which I'm going to use as black, is delta v. And that is dv, which is equal to the acceleration vector, dt. And really, this is the acceleration vector too, in this case. But I like to be more appropriate. It's actually acceleration delta t. So if this took place over a longer period of time, and there were, this is initial velocity and this is the eventual final velocity vector, you would have to take into account the delta t. But since the acceleration vector is only happening from 1 second to 2 seconds, right? This is the initial velocity vector, and then the acceleration vector gets added to this, right? Right. So if this is the initial velocity vector, let me actually grab this again, and I want to prove something to you. I'm going to redraw the positive. I'm going to draw the positive initial velocity vector, which is down and to the right. I'm going to make it green. Okay. Right. So this is the positive initial velocity vector. Why is that doing that? Courier. There we go. This is a positive initial velocity vector. And what we're going to do is we're going to add to that this acceleration vector. All right? So I just copied it and I pasted it right here. And hopefully, since V final, so what I'm thinking is this. Since V initial plus acceleration delta t is equal to V final, and this is the acceleration vector, right? And I'll just put that right there, right here, that this is the acceleration vector in this case. Since the acceleration delta t is taking place from 1 to 2 seconds, right? So that acceleration vector is only adding at the 1 second mark. And so what you find out is that this final velocity vector should be the resultant vector which it is, of this vector addition of the acceleration vector and the initial of the acceleration vector and the is this final velocity vector is a resultant of the initial velocity vector and the acceleration vector. Okay, so there's a couple ways to do this, but I kind of like the process that gets laid out right here in Knight's book. Just take the initial velocity vector, reverse it, and then add that to the final velocity vector. And that'll give you the change in velocity. And if that is basically taking over the, if that's only at one time interval, then that change in that velocity vector will also be the acceleration vector, as long as that's delta t is, 1 second. Okay, it's applying at that acceleration vector is being applied at the 1 second mark, which is right here. And now let me just lay that out again here. 0 seconds, and then 1 seconds, and then you're adding that and the acceleration vector, and then what will happen is you'll eventually end up right here, right? So that means over the period of that 2 second mark, you went from right here to here. Okay. All right. Over the period of that 0 second mark, you went from here, and then it actually went from here to here, and that acceleration vector took place over the 1 second to 2 second mark. Okay. Moving on. All right. Suppose you're given a similar problem where you're given an initial velocity vector and a final velocity vector, and you had to find the displacement of the particle of what's happening here. So you had an object that started here, it moved to the right over the period of 1 second. So that's the initial velocity vector. And then something happens, and then you have a final velocity vector right here. Can you, by just using logic, identify the displacement, the overall displacement of the particle? So pause the video now and see if you could do that. So just by logic, if you think about it, if you started out here at the 0 second mark, you moved to the right over 1 second, and then you move down and to the right over 2 seconds, then essentially you started here and you ended here. So isn't this just the displacement of the particle? I mean, right? Isn't that just the displacement of the particle? And I'll write that here as dr. R is the, again, R is in place, it's a placeholder for x, y, or z. But in our case, since this vector, this black vector, has components of x and y, we're going to use delta r. So the particle started here and it ended here. Okay, so the displacement of this object is basically this entire line, right? And so what you could say is this so when you think about it, we had an equation of motion that was delta r is equal to, or the displacement vector is equal to v final plus v initial divided by 2, which is the average, by the way, this is the average velocity vector, and that's delta t. So really, delta r is equal to the average velocity vector, delta t. Well, that's kind of what we did here, right? We added this vector to this vector, so we did v final over v initial, and divided it by 2, but that delta t took place over 2 seconds, right? So even though we're dividing it by 2, we're then multiplying it by 2 seconds, right? So there you go. So basically, the average velocity vector, is basically analogous to the delta r vector, right? They're certainly in the same directions. Now, obviously, if you have a final velocity vector that took place over the 3-4 seconds mark, and you have an initial velocity vector from the 0 to 1 second mark, well, now that 2 isn't, so since in our case this change in velocity took place over from 0 seconds to 2 seconds, right? So this is 2 seconds divided by 2. So basically, delta r is equal to just v final plus v initial, right, in our case. All right. However, that is not always the case, right? So what happens if your initial velocity vector is given from the 0 to 1 second mark, and then you have a final velocity vector that is from the 3 to 4 second mark, right? Well, now your delta t is going to be 4 seconds minus 0 seconds, right? So what that means is your delta r is going to be equal to v final plus v initial over 2, and that delta t, which is 4 seconds. So now you're going to have to so you're going to have to go 2 times v final plus v initial, right? So you're going to have to basically double the initial velocity vector. So that looks about double this, right? Initial velocity vector plus initial velocity vector, and add that to the double of the final velocity vector. Final velocity vector plus final velocity vector. And that means this displacement vector, for this case where you're given an initial velocity vector and from 0 to 1 seconds, and a final velocity vector from the 3 to 4 second mark, 0 to 1, and a final velocity 0 to 4 second mark. Anyways, so this displacement vector is going to be a lot bigger, right? It's actually going to be 2 times our initial delta r. So you do have to consider delta t when you're doing things, right? It's not so simple. That's why I was a little leery about, in this case, to just call this the acceleration vector. It's actually the acceleration delta t vector. Again, because if you're given a final velocity vector from the 4 to 5 second mark, and this is from 0 to 1 second mark, well, now you have to consider that delta t. It's actually going to be important, right? In the case that we did up here, we're only considering 0 seconds, 1 second, and 2 seconds, and since the acceleration always acts at the 1 second mark in this case, then delta t was just 1 second, right? Anyways, so this is how you find a particle's displacement vector, okay? You're basically doing a vector manipulation through algebraic using the equations of motion, and there you go, okay? And this is just to emphasize what we just did. Again, the average velocity vector, which is final velocity plus initial velocity divided by 2. That's what they mean by average velocity vector here. Okay, that is equal to delta r is displacement over time. Okay. So there's a lot of ways, there's a lot of tools that are at our disposal, okay, when we're doing these types of problems, right? And they all start with our equations of motion. And then what we're doing is applying the equations of motion to a given set of vectors that we're given. And so a given set of vectors. And then what we're going to do is manipulate the equations, which then we in turn would be manipulating the the vectors to fit some solution, okay? And so that's what the lecture tutorial 1.3.3, Kinematic Equations 1, is all about, right? And I love this problem because it's kind of breaks out from what we were just doing, because you have to consider in this first problem is delta t takes place over 4 seconds, right? And so here you're given an initial velocity vector from 0 seconds to 1 second, and then this is going to be a final velocity vector, which then has to be taking place from 3 seconds to 4 seconds, right? So we're missing a vector in this part, right? You have an initial velocity vector, and you have a final velocity vector, and this is over a period of change of t, so there's a missing velocity vector somewhere in here, right? So what we're supposed to do is we're supposed to find the final velocity vector, okay? So why don't you give it a try, and using what we just studied, and pause the video and try this out, and just, you're going to have to consider the fact that there's a delta t. So try to write your equations of motion and see which one fits to find what delta r is, okay? Pause the video now. Okay, well, let's go ahead and let's get ready to copy some vectors here. But before we do that, let's think about what we have to do. So we have to do some sort of vector addition, right? And when I think of displacement, I think of our curvilinear equation of motion, which is going to be delta r equals VIT plus 1/2 AT squared, right? The problem is we don't have an acceleration vector. So that's not a good way to go about doing this, right? So that's not going to be helpful. The best thing to do is do what we did in the last problem, which was right up here, right here, and consider this equation here. So consider the manipulation of the curvilinear x versus t curve fit and integrated with the linear fit of the velocity versus time graphs. And when we do that, we got this. Delta r is equal to v final plus v initial divided by 2, so the average velocity divided by 2 delta t. Okay, so in this case, delta t is going to be over the period of 4 seconds. So v final plus v initial divided by 2, and delta t is going to be 4 seconds. So what we're going to get is 4 divided by 2, which is going to be 2 times v final plus v initial, which is then equal to 2v final plus 2v initial. So to get delta r, we have to double the final velocity vector, and we have to double the initial velocity vector. Okay? So let's try it out. Let's see what we get here. So we did our algebraic manipulation. So what I'm going to do is I'm going to match up the initial velocity vector, and I forget we use green, right? Green is our color for the initial velocity vector, right? And then I'm going to grab our final velocity vector, and I'm going to go ahead and drag this here, drag it here. I'll do a better job at lining that up. And I'm going to call that blue. All right. So that's our final velocity vector. Okay, and it should be pointing straight up. Okay, so we have our initial velocity vectors and we have our final velocity vectors. Okay, so what we have to do is double this, right? So we have to take our initial velocity vector and we have to double it. So now this is 2 times the initial velocity vector. And then we're going to have to take the final velocity vector and double it. So I'm going to align this, and then I'm going to align this. I'm going to put some labels on some things too, right? Because again, delta r is equal to 2v final plus 2v initial, in this case, since delta t is 4 seconds. So this is going to be the initial velocity vector. And I better indicate that that is a positive initial velocity vector too, because sometimes we have to reverse our velocity vectors to get, right? So this is the initial velocity vector, and this is another one of those. And then this is our final velocity vector over here. And this is another final velocity vector here. So by doing this, we could see that our total displacement vector over this entire period of time which is delta r, is equal to 2, come on, drag this out here, 2v final plus 2v initial. Okay, and in this case, this is our resultant vector of this. Okay, so that's kind of how to do these problems. You're supposed to you're basically supposed to use the equations of motion to help guide you, and then Mark always throws in a curveball, which is he's changing the time. So you're going to have to consider the delta t here on the problems that he's given. Okay? Let's move on. One thing that you need to really learn here is that the velocity vector is always in the equation, is always in the direction of motion. But the acceleration vector can be pointed in any direction. And again, it's pointing in the direction of delta v, or the change in the velocity vector. But suppose you had an object, and this is a y versus x graph. So we're looking down on an object that is moving this path. So imagine you're overhead looking down, and maybe this is a forest path, and you're seeing a winded forest path. And a person, so the velocity vector will always be tangents to the direction of motion, right? So right here, the object right here, you draw a tangent line, and that is your velocity vector at this point right here. At this point right here, number 2, you draw a tangent line right here. And I'll just grab a little tangent line, we'll overlay it right here. Okay, and so if you see that, how that's a tangent line to the point at number 2, well, that is the velocity. That's the direction you're moving down and toward the right at that point. Well, now you're moving up here, and so at this point, point 3, I'm going to draw another tangent line right there, and that means you're moving up and to the right there. And at 4, it looks like 4, the tangent line is going to be right about here, right? So I'm just considering tangent lines for the direction of motion, okay? Well, even though you know the direction of the velocity vector is always a tangent line, the acceleration vector can be pointed anywhere, okay? And the acceleration vector, if an object is speeding up, again, let's review. If an object is speeding up, then the velocity vector, if an object is speeding up and the velocity vector is this way, that means the acceleration vector is going to be in the same direction. So that's speeding up. And this is VI and A, same direction. However, if your velocity vector and acceleration vectors are pointing in opposite directions, for this, you're slowing down. So opposite, this is slowing down, right? So if this object was on a track now, if we consider this as a track and we're looking at it from the side, well, the object would be, at this point, be moving down the track here, and if it's on a track right here, it would, and it's speeding up, that means it's going to have an acceleration vector pointed in the same direction that it's moving, right? And then at this point right here, if it's still speeding up a little bit, it's going to have an acceleration vector pointing in the same direction that's here. But the problem is it's curving, right? And so if you need to turn, your velocity vector is going to be perpendicular to your acceleration vector, right? And then you will turn, right? So we kind of did that a little bit in the one-dimensional motion stuff. We talked about what turning around is, or in this case, turning in a circle means if your initial velocity vector is perpendicular to your acceleration vector, you're not going to be speeding up nor slowing down. But what will be happening is you're going to just turn to the left. So that means you'll be traveling in this direction, right? And this vector is the same size as this vector. Well, if you have another acceleration vector pointed to the right, the same amount, well, now you're going to have another velocity vector which will be pointed this direction, right? And so now at this point, you, oops, that's too big of a vector here. And so This is another velocity vector. Well, you're going to add that same acceleration vector here, right? And so that acceleration vector here, well, now you're going to be pointing in almost this direction. So it just keeps adding, and eventually what happens is the object starts moving in a circle, right? So at this point, if you're moving up here, you are going to be accelerating towards the center of the circle there. And then add these two up, what eventually happens is you'll be moving to the right here, and then you add an acceleration vector to that, which is essentially an acceleration towards the center of the circle, and now you're moving, and now you're going to be moving down right here at this point. At this point, if you're moving counterclockwise around this circle, your velocity vector will be down, your acceleration vector will be the center. Which kind of makes sense, right? Because if you got in your car and you started turning your car counterclockwise, wouldn't you feel the right side of the seat belt pulling you in? Your body wants to move at a tangent to the circle, but the seat belt keeps pulling you towards the center of the circle. And so this is what turning is. If you're turning, which means you're not speeding up nor slowing down, you're just changing your acceleration vector, which means this, your velocity vector and your acceleration vector are perpendicular to each other, which means you'll have a constant speed, but you're still accelerating, which is weird. So this is just called turning. Well, at this point right here, you're still kind of speeding up in that direction, but you're also accelerating towards the center of the circle. So the point of this slide right here is to kind of, you got to start thinking two-dimensionally, which means you could have velocity, two different acceleration vectors pointed perpendicular to each other. If you're speeding up as you're going down this hill, that means your acceleration is pointed in the same direction of your velocity vector here, but then since you're turning, since this path is like a circle shape, you're also going to be accelerating up into the center of the circle point too. Okay? And then your overall acceleration would be the acceleration there, plus your acceleration towards the center of the circle, which means your net acceleration is going to be that direction. Okay? Well, let's apply it. So suppose you had a ball rolling down a long hill through a valley and back up the other side. What you're supposed to do is draw a motion diagram of the ball, showing the ball's velocity vectors and acceleration vectors at all points through this. So what I'm going to do is I'm going to basically just say the ball is rolling down a hill and it's going to be rolling back up another hill over here. Okay, so this is the path that the ball is moving. And I wish it was more bowl-shaped. Let me redraw that. There we go. Still a little bumpy, but that looks good. So your ball starts here, and it's going to end here. So what I want you to do, I'm going to pick little dots, and I want you to draw the velocity vectors and acceleration vectors at each one of these points. And you might actually have two acceleration vectors that are pointed perpendicular to the direction of motion. Okay, so let's go ahead and do it. So go ahead and pause the video, and I want you to draw the acceleration vectors and velocity vectors at each one of these points, and let's see what you come up with. Now remember, when it's going downhill, the ball is speeding up. When it hits the center here, it's probably going to be moving for this instant at a constant velocity. And then as it starts to go uphill, it starts to slow down. Typically, a constant velocity or a constant velocity vector takes place when you go from speeding up to slowing down, or slowing down to speeding up. Usually something happens weird at the very center mark, okay? So let's go ahead and try this out. I'm going to put little times on this. Oh, it should be 3 seconds, 4 seconds mark, 5 seconds mark, 6 seconds mark, 7 seconds mark, 8 seconds mark, and 9 seconds, right? So go ahead and try drawing those velocity vectors and acceleration vectors. Let's do it. well, here we go. Let's go ahead and draw the velocity vectors at each one of these points. And I'm going to just free draw this, which is probably a mistake, but I'm going to use let's use blue for the velocity vectors, okay? So I'm going to look at tangents to the circle. So this object right here looks like it's moving down and to the right at that point, right there. So I'm imagining a little tangent to the circle at that point. At this point, it looks like it's moving that way. This point looks a little bit more. This point a little bit more. Here, it looks like it's level. Here, it looks like it's moving up and to the right. More up and to the right. More up and to the right. More up and to the right, and more up and right. And I didn't space these out properly, but I just I'm focusing on drawing the velocity vectors at each one of these points. So velocity vectors are always tangents to the direction of motion, or to the path of motion, right? So tangents to where you are on this path right here. Well, if you think about it, the acceleration vector at this point, you would be speeding up as you're moving downhill, and you'd be still speeding up, and you'd still be speeding up, right? So this is the acceleration vectors. So if you're speeding up, you have to be, and I'm not trying to be worried about the size of these vectors. I'm just thinking in terms of speeding up, slowing down, constant velocity. So when you're going downhill, you're speeding up as you're going downhill. And then I think what happens when you hit the level point right here, your acceleration is 0. Okay? Right? So on level ground, if you're moving on level ground, and the ball is just freely rolling, there's no force or anything driving it, then that means you have no acceleration. You would be moving at a constant velocity. And then at this point, it looks like you're moving up and to the right, and then up and to the right. Oh, I'm sorry, you're moving up and to the right, but since you're going uphill, your acceleration vector is going to be pointed downhill. Okay? And then downhill there, right? But there's also something else going on here too, right? Since you're turning in a circle, and since we just talked about it, you're going to have an additional acceleration vector perpendicular to the direction of motion. So you actually have two simultaneous acceleration vectors. You have one in the parallel to the direction of motion, and that's the speed up, slow down acceleration vector, right? But now you have an additional acceleration vector. I'm going to attach it to that, which is pointed perpendicular to the direction of motion. Anytime you go in a circle, like we talked about over here, anytime you go in a circle, and since this path is circular, you're always going to be accelerating towards the center of that circle at this point. So I'm imagining a line parallel to the path of motion. I'm going to just add that acceleration vector here. And so if you think about it, you're always accelerating towards the center of the circle. And at this point, even though you have a constant speed right here, you're still accelerating towards the center of the circle. And then here you're accelerating towards the center of the circle, and here you're accelerating towards the center of the circle, center of the circle, center of the circle, so perpendicular. And that's what turning is. Anytime you have to turn a car, turn around, you have to have a perpendicular acceleration vector. Well, what that means is the addition of an acceleration vector with another acceleration vector is going to yield a net acceleration vector, right? So that means you have two acceleration vectors happening on you all the time throughout this here, except for at the center. And that's going to yield an acceleration vector, two acceleration vectors. Well, that means you're going to have a net acceleration vector, which is the addition of those two vectors. And I'm going to use black for that. Okay, and here the net is just the same thing as this acceleration there. Here it's pointing up and to the left, and it's pointing more up and to the left, and looks like it's getting more leftwards pointed the more we go. And so the addition of those acceleration vectors is the direction of your net acceleration at that point. And so when we go on to how Knight presents the problem, he's giving you the acceleration vectors in the direction of motion. If this was on a straight line, it would just be like this. We had a curve through the entire time. But then at this point, you actually do start to curve. And notice the acceleration vector is pointed up and to the right, which is really similar to ours right here. Okay. And then here, the acceleration vector is just pointed up, and that's because at this center point, you're not speeding up nor slowing down. You're only turning, which means your velocity vector would just be pointed just to the right here. Up. Oh boy, that's a terrible line that I drew. Sorry about that. So at this point right here, you'd just be moving to the right, but since your acceleration vector, so your velocity vector would just be to the right, your acceleration vector would be directly upwards, and that means you're just turning. You're not speeding up nor slowing down. And so notice that this line is this net acceleration vector is pointed up and to the left, which is the same thing that we drew right here. Okay? So what you're supposed to do is apply what we just did to this case in the lecture tutorials. Okay, so I want you to go ahead and try this out on your own, and then what we could do is we could talk about it, and we'll do a couple of these when we go through after we so go ahead and pause the video and try this out. So you're going to have to draw the velocity vectors and then the acceleration vectors as far as the speed up, slow down acceleration vectors, and then also draw the turning vectors because there's some circular parts. Okay, so try that out. What I also want you to do is to describe this in terms of speed up, slow down, constant velocity as well. Okay, so draw vectors at each one of these points. Pause the video now. All right, we are back. So I'm going to start off by drawing the velocity vectors, and I think I like to use blue for that. Well, in this case right here, at A, this object is on a frictionless slide, so it's going to go down this right here. I'm kind of reading this. When it gets to B, it's now on a flat level plane. And then when it gets to C, it's kind of curving, so there might be, since there's a curve to this, there might be an acceleration vector in towards the center of this circle. And then it hits D, and then there is another different circle here. And then when it gets to E and F, you have another circle here. So basically C, D, E, and F are going to have two acceleration vectors, but A is going to have only one acceleration vector and B is. So let's start off by drawing just the velocity vectors, which is tangent to the direction of motion. So my velocity vector is blue, which is going to be pointed down and to the right here. And I'll draw it above this. So this velocity vector is down to the right. I'm labeling it with a V. At this point, the velocity vector is just to the right, and a tangent to a straight line is just parallel to the straight line. Okay. At C, a tangent to this circle looks like it's that direction. At D, it looks like it's just to the right. At E, it looks like it'll be going up and to the right. And at F, it'll be going just to the right. Okay. Well, now let's think about the motion that we're doing. Okay. Let's think about the motion here. If it's sliding down A, it's going to be speeding up at A. At B, it looks like it's going to be a constant velocity because, again, it's not going to be on a level plane if you have nothing driving it nor for slowing you down. You'll just slide forever in a straight line. At C, it looks like it's going downhill, so it's going to be speeding up here. At D, it looks like it's going to be, it'll just be turning, but it'll be at a constant velocity. Well, a constant speed, I should say. You still have an acceleration vector. At E, it looks like you're going to be slowing down. And at F, it looks like it's changing from slowing down to speeding up. So again, this is just turning. So I'm going to just put turning here. And it's a constant speed. Okay. So now I've kind of categorized this. Now that's going to help me draw my acceleration vectors. And I'm going to be drawing two acceleration vectors when I can. In this case, since I'm speeding up, that means I'm going to have an acceleration vector in the same direction as my velocity vector. Okay. Here, so I'm speeding up as I'm moving downhill. That means I have two parallel vectors, a velocity vector and acceleration vector, pointing in the same direction. At B, I'm just traveling to the right at a constant velocity. That means I have no acceleration vector. At C, it looks like I would probably be speeding up, so my acceleration vector and velocity vector would be in the same direction. At D, I'm just turning, so I'm not speeding up nor slowing down, so I'll have a zero acceleration vector as far as a linear is the same line as a velocity vector. And at E, I'll be slowing down, so I'll have an acceleration vector opposite the direction of my velocity vector. At F, I'm going to have a constant speed. That means I'm going to have no acceleration vector that's parallel to my velocity vector. All right. Now let's talk about our turning vectors, which are our perpendicular vectors to our velocity vectors. Well, A is going in a straight line. B is also a straight line. But at C, if you can imagine, this looks like a circle, like a mini circle right here. That means you're going to have an acceleration vector. I might need to erase something here. I might need to erase this and kind of move it a little bit. I'm going to redraw that up here. So I have an acceleration vector in the same direction as my velocity vector at that point, right? But since I'm moving in the circle and you're going to have an acceleration vector towards the center of the circle, you're going to have to add that to that acceleration vector, right? So this acceleration vector towards the center of the circle is this same one. And I just add that to my linear acceleration vector. Okay, I hope that makes sense. D looks like it's a part of a circle here too. And that means, again, if you're moving to the right, and that means you'd be kind of moving counterclockwise at this point, the center of the circle would be straight up. Okay. At E and F, there is a circle right here. It looks like a circle. So at E, center of the circle would be down and to the right, which means I could draw it right here, down and to the right. And at F, the center of that circle is just going to be straight down. So that acceleration, linear acceleration vector anyways. So now let's go ahead. So this acceleration vector is just going to be a turning vector since we have a constant velocity at F. So now let's draw our net acceleration vectors to these guys. Well, this net acceleration vector is the same thing as this one, since the object is speeding up and it has no turning. This one has no net acceleration vector, so that is going to be 0. So a net is 0. The net acceleration vector here is going to be the addition of the two acceleration vectors here. So a net is going to be down and to the right. Here, the net acceleration vector is the same direction as the one acceleration vector at D. At E, you have a down into the right acceleration vector added to a down into the left acceleration vector, and you'll get a net acceleration vector in that direction. And then at F, since we only have one acceleration vector, A is equal to 0 plus A down is just A down. So A net is going to be in the same direction as that. So that's an example of each one of how you're supposed to approach this tutorial. Okay? So please do your homework, please do your reading, and then go ahead and start on these tutorials. I hope you had fun. Bye.